if you haven't yet, take a second and look at this practice problem. This is a jog your memory from last Thursday. You are given the scenario. In the flask, I have already put in a half atmosphere of A and a half atmosphere of C. I then add some solid B, and we are working off of this reaction up here that A plus B goes to 2C. I give you the Kp, so you have the equilibrium value, and I'm wondering, as this system approaches equilibrium, to get there, will I make A? So will the pressure increase? Will the pressure decrease? Am I going to lose some A to get there? Or am I already at equilibrium and I don't need to change the pressure of A? So take a second, work with the people around you, come up with an approach. And in a minute or two, I will ask you if you got 1, 2, or 3. Ooh, that's loud. All right, I'm going to add another option here. All right, so 1, 2, 3, or 4. Which one did you guys pick? Let me see. Okay, excellent. All right, so let's tackle this together. All right, this is a sneaky Q question in that I didn't ask you to calculate Q, which is our reaction quotient, but that's what you should do, okay? So to know whether or not we need to make more A or make more C, we need to compare these initial conditions. So we're going to calculate Q, the reaction quotient, and see if it's bigger or smaller or equal to this Kp that we're given. Okay, so a good first step is to write down what does Q equal. Okay, so you'd say, okay, Q equals the pressure of C, that's squared, right, because I got 2 of them. And then I'm going to divide by the pressure of A. And you will remember that because B is a solid, it's a pure solid, it doesn't show up in our Q and Kp expressions. All right, so the fact that I have 4 grams there, I don't need to do any 4. The really significant thing is that at the end of the day, I have some B left, which means that I have established equilibrium. But I don't care how much, I just need to know that it's there. Okay, so then I plug in my values at these initial conditions, which are maybe not at equilibrium. I've got 0.5 squared divided by 0.5. So my Q is 0. Okay, now I say is 0.5 greater or less than 0.24. Okay, so I find that QP is greater than KP. Okay, I have too much C. That Q number is too big. That means my numerator is too big, or I could say my denominator is too small. At the end of the day, I need to make more reactants to reach equilibrium. So translating that into these options, I'm going to see the pressure of A increase as this system approaches equilibrium. Okay? So when you are given conditions that are not equilibrium, and you're asked, what direction is this reaction going to go? Is it going to go forward? Are you going to make more products? Or is it going to go backward and make more reactants? It's a Q question. Okay? And Q has the same expression as K, but you can use non-equilibrium values. All right? Good? Okay, then let's move on. I got a little bit more review that we'll look at. Okay, so that was this. We just did this part of what can we do with an equilibrium constant. So we knew what the equilibrium constant was. It was 0.24. And then we can make predictions about, hey, when I mix this amount of stuff together, I think I'm going to make more product or I'm going to make more reactant. That's what we just did here. So this first place is a Q versus K. All right. Then the next thing we can do, if we know the equilibrium constant, then we can actually calculate how much stuff we should have at equilibrium, which is really useful because as chemists, we want to know how much we're. All right, so we left off here on Thursday. All right. And this was the slide that I left you with, right? So we set this up, all right? A similar reaction here where CCl4 degrades into carbon, which is solid, and then 2Cl2, all right? And then I tell you that we have some amount of CCl4 to begin with. That was our 3. And we know that to reach equilibrium, I have to take some of that CCl4 and turn it into our carbon and Cl2. Okay, so we set up our ice table. And it's like, okay, well, what am I going to do with this ice table? I don't have values for the equilibrium numbers yet, but you have, let me annotate this with a different number. We were able to express the equilibrium values using one variable, right? That X. So when we take those numbers and plug them back here into our expression, and we know what it equals because we've been given this value, we now have one equation with one unknown, which is solvable. In this case, and sometimes when you're working in Pearson, you are going to have to solve the quadratic. I don't ever want you stopping and getting out your quadratic formula and doing this. I just want you to either plug that into your calculator, go to Wolfram Alpha online, plug that in, and just have it solve it for you. Unless you're like, I love doing this algebra, we're not going to ask you to do it on the exam, okay? So I'm going to show you the 2 workarounds that we might give you on the exam to avoid the quadratic, okay? But at this point, if I was working on the homework and I got to this point right here, this is when I say I'm going to go to Wolfram Alpha and just type that in and ask for X. Okay, I'm not going to solve that math myself. I know I'm not going to have to do it on the exam. Okay? Again, happy if you want to do it yourself, but no one's going to ask you to do it on the exam. All right? Here are our 2 workarounds. Okay, so the next 2 slides are called avoiding the quadratic. There's 2 different ways. All right, so let's set this problem up together. We have a reaction flask, and we charge it with 0.5 molar O2, and we have 0.5 molar N2, all right? So I have equal concentrations of my 2 reactants, and assuming I have no product right now to start with, that's a good assumption, and I have Kc, right? I know the equilibrium constant, and I want to know how much NO am I going to make. All right, so let's set this up. Kc equals, and that's a big K, all right? We have the concentration of NO squared divided by N2 times O2. We know this equals 4.17 times 10 to the negative 4th. Okay? So our goal is to find this number here, we want to know that. What's that number at equilibrium? Okay. We don't have any equilibrium values. We only have initial values. So let's set up an ICE table. Initially, we have 0.5 of each of these and none of that. Okay? I can tell you what the change is using my balanced reaction. I know that I'm going to have to take a little bit of NO to make it 2x, right? Because I've got a 2 here. Every time I lose one N2 and one O2, I'm going to make 2 of my NO. Okay, so at equilibrium, 2x. Okay, now I can take those. Those are my expressions and plug into my KC. All right, I'm going to take these and I'm going to put them in here, right? So I'm going to have 2x squared. And on the bottom, I have 0.5 minus x, and that's also squared. Right? Because I've got 2 of them, and they are the same. And I know what this equals. It equals the 4.1. All right. So I might look at this and say, rats, I need to expand that bottom. I'm going to wind up with an x squared and an x. So I'm going to wind up doing a quadratic. Okay? And you could do that, and you could get the right answer. But it would be a lot of extra work that you didn't need to do. This is called a perfect square. Okay? I can take the square root of both sides and get rid of my squares on that x. So take the square root of both sides. I'm going to wind up with 2x over 0.5 minus x equals the square root of that 4.17, which I have written down somewhere. 0.0204. And now I don't have an x squared term, and this is relatively easy algebra to solve out for my x. Okay? So look for that trick. Okay? This is a good way to avoid having a square. So what I'm going to do is I'm going to multiply both sides by 0.5 minus x. I'm going to go through and solve out for x. All right. And I'll have 2x equals 0.0102 minus 0.0204. All right, and there's an x there. Okay, so I'm going to add to both sides, isolating my x's. All right, divide both sides by that 2.204, and I wind up getting an x equal to 0.005. All right, and then this, it's still a relatively long process. So on the exam, you might be really tempted to be like, I got to x, I'm done. If this is a numerical question, I'm going to type in 0.005. And then you're going to get the answer wrong, because we weren't asking for x. We were asking for the equilibrium, and I should have written concentration here. My bad, guys. Concentration, because I was in concentration for my others too. I was asking for the equilibrium concentration of NO, which is 2x. So I found x, and now I got to plug it back in. Okay, my equilibrium concentration of NO is 0.01, 2x. So don't forget that last step.
Writing off the ice tables, as long as the sides equal on one side, you can technically put whatever, right? You could do it's I know we're a losing reactant, but since it's at equilibrium, if you do plus and plus on one side and then negative, it just has to match on one side.
Oh, Oh, I see what you're saying. Yeah. So in the like, why did I decide minus on one side?
Like, I understand reactants you're using, but like at equilibrium, it's going back and forth.
Sure, sure. So the question is, in this case, why do I have minus here? This is a good question, and we can do an example after this. All right, so in this case, I don't have any product to lose. I am required to make more product here. But if I had a balance of both reactants and products and was wondering which way is it going to go, then that's actually kind of a Q question. I would need to figure out what direction it's going based on Q, and then I would use the right sign, the signs based on that. But yes, the reactants both either have to gain or they both have to lose, and same on the other side.
So that's where you get the sign from?
Yeah, the sign. Am I going to gain some reactant or am I going to lose it? In this case, we're losing it. I have no other option, and I have to gain some product because I don't have any to begin with, and I've got to have some.
Would it change your answer?
So if you put in the wrong signs in a table like this, so let's say I said plus x and minus 2x, I would have wound up with a negative. I would have solved for a negative x. And then the negative and the negative would have canceled. And you would be like, oh, that was a positive number. So I have a specific example we can look at after this. Okay? So this is the one trick that we can use to avoid the quadratic. Okay? We'll set it up so that you can take the perfect square. Okay? There was an example like this on the recitation worksheet on Friday. Okay? All right, the other option. All right, so here I have the same exact setup, and I will immediately correct myself here. This should be concentration. All right, but now I haven't started with equal amounts of O2 and N2. All right, so that's going to be problematic for us when we want to take the perfect square. So KC, we still have the same expression. Still equals the same thing. But now, when I set up my ice table, and I think I set it up this way before, so I'll stay consistent. Now I have 0.6 of my N2 and 0.4 molar of my O2. So when I go to put in my change, okay, this is also the same. I still have to make some NO, right? I am not going to wind up with the same expression for N2 and O2. Okay, so I've lost the perfect squareness. Okay, because when I plug this in now, I'm going to have 2x squared over 0.6 minus x times 0.4 minus x. Right? So I don't have that square in the bottom, which is what made it so nice on the previous slide. Okay, so how can I make this math easier for myself? All right, and this is not a math trick, this is an assumption. All right? When I look at that KC value, I see that it is very small. Right? So times 10 to the negative 4. So 0.000417. This is a small number. How can I interpret that? A small number means that at equilibrium, I'm going to have a very little amount of product. Yes? Small k, very little product. Okay? Very little product. That, yes, and it's not just less than 1, it is really small, right? It's 0.000417. All right, so I'm starting here with all reactants. Okay, that means that to get to equilibrium, I only need to make a tiny amount of product. I am actually, with these starting conditions, I am actually quite close to equilibrium. In other words, x is a small number. Okay, the change that needs to take place is small. Okay, and I did that analysis because I know that KC is a small number. That means I should have mostly reactants. That's where I'm starting. I am starting with only reactants. So this change is small. Okay, this is an assumption here where I now say if x is very small, that means that I can really call this 0.6, right? I'm thinking x is going to be a very small number. So 0.6 minus 0.0001 or whatever is basically 0.6. Okay, that's the assumption that I'm going to make. And I'm also going to do that for O2 and say it's really small here. I can't make that assumption here, right? When I have just 2x, I still need to hold x there. But when it's in comparison, when I'm going to take a difference, when I'm going to use x as a minus or a plus, now I'm saying that that is negligible. All right? So that's the assumption. And we'll test it. We'll make sure we'll come back at the end and say, was that a good assumption? So I'm going to say 2x. All right, now I'm going to put that into place here. Okay, so I'm putting my assumption into place. I'm going to have 4x squared over 0.6 times 0.4. Now my math is very simple, right? I'm just going to multiply both sides by 0.6 and 0.4. Divide by 4, take the square root, and I find that x is equal to 0.005. And here's where I go back and say, was this a good assumption? Is 0.005 much less than 0.6? Yes. And the rule of thumb that we will wind up using is it less than 5% of the number? Okay, and we're going to we're only going to use this assumption in chapter 16. Every single problem, we're probably going to make this assumption that x is small. So this is a good thing to get comfy with now, that yes, this number is much smaller than these two numbers by a factor of 100, okay? So I can go back and now say, yeah, that was a good assumption, and I think at the end of the day, I'm going to make 2 times 0.005, and I'm going to have 0.01 molar. And that's a little bit of an approximation, but it's good enough. Okay? So look out for these opportunities in Pearson when you have very small Ks or very big Ks. If it was a very big K and I started with 100% product, x would have been small in that scenario too. Okay? Okay. Can I get, by show of hands, do you want to do another example problem of one of these? Okay, don't be shy, because I'm going to totally skip it if I don't see enough hands. Okay, let's do one more, okay? All right, I'm going to go back here, use this space, okay, on slide 4. We're going back to our jog your memory problem, okay, where I had A plus B, which is a solid, is in equilibrium with 2C, which is a gas. All right? You guys calculated Q, right? That was how we started this. So I want to know at equilibrium how much A, well, let's see, let's write, what is the pressure of A? All right. We started with 0.5 atmosphere of A and C, and we know we have excess B, okay? And Kp was 0.24. All right? So in the first question, all we said was that A increased. Okay, we know based on Q, we said, hey, Q is actually too big. I need to make some more reactants. So we said that the concentration or the pressure of A increased, but we actually could have said exactly how much, okay? So set this problem up as an ICE table. You know your initial values. You know what we're going to set it equal to, okay? And you are going to run into the quadratic formula. So at this point, I just want you to set up Kp in terms of x. And let's make sure that you have the right expression for Kp. All right, give me a thumbs up if you have Kp in terms of x. Is that okay? All right, so this is my setup. And if we had not done our jog your memory, I would have now, when I get to my change row, I would have needed to do that analysis. Because off the bat, I can't look at this and just know which way it's going to go. I need to know what Q is, right? To make the assessment on the sign here, am I going to make more reactant or more product? I need to know how Q compares to K, right? We found that Q was greater than K in our opening problem. So that means I need to make more A, so I should have a minus 2x here, right? I could have, to be fair, I could have just guessed at the sign, and then based on like whatever the quadratic formula spits out, I would have known that I had gotten it right or wrong in terms of direction based on that sign. It feels better to know, hey, I know the direction of this reaction. I'm going to reflect that in the signs here. So at equilibrium, I'll have 0.5 plus x, and I'll have 0.5 minus 2x, okay, for C. Now I'm going to plug it into Kp. And that's going to be 0.5 minus 2x squared divided by 0.5 plus x. All right? That was the point I was hoping we could get to. And this would be then the point where I'd go to Wolfram Alpha, or I'd pull out my quadratic formula like program, and I'd plug this in, and I'd find x is equal to 0.066. Okay? There was one other solution, obviously. There's going to be two. I think the other solution was like, I don't remember exactly what it was, but it was something like this, and I would have looked at that, and I can eliminate that as a reasonable answer, because if I have 0.5 minus 2 times 0.49, I'm going to wind up with a negative amount of C, and that doesn't make sense. So you pull, there's going to be one answer from the quadratic that makes sense. Grab that one. In that case, that was this one. Don't quote me on this. I'm just, I think that was about what it was. Take that number and I put it in here. And I say, oh, I know that A increased, and now I can tell you that at equilibrium, the pressure of A was 0.566. atmosphere. Okay? So again, this is like harder than what you would see on the exam in terms of the math that you'll encounter. But the concepts of saying like what direction is it going to go? Am I going to see an increase or decrease? This is all fair play. And then you'll see one of the two options where we either give you a perfect square or we've set it up that you can make the assumption that x is small. Okay? Yeah.
So if we started with more reactant, or we had more reactant, it would be positive on the reactant side?
If we had started with more reactant, then we would have had a Q that was too small, and we would have subtracted, we would have converted some reactant to product.
So we made it positive on this top.
But we made it positive because we knew that Q was bigger than K from what we did in the first slide of class. That means that we have too much product to start with and need to make more reactant. Yeah. Okay. That's what we can do with K. Those are our two things. We are now wrapping up chapter 15. This is Le Chatelier's principle. All right, so if we have a system, let's set this up. If we have a system and it's at equilibrium, and then we do something to mess with it, these are the things we can do to disturb it. Okay, these are the disturbances. All right. We can change concentrations, we can change the pressure via volume, or we can change the temperature. So we do something. The disturbance now means that Q doesn't equal K, and so the system will then respond by going back to K, by taking Q and going back to K. So we have an initial system. We've let it equilibrate. Q equals K. We mess with it, okay? Le Chatelier's principle requires like some outside interference, okay? We mess with the system. By doing that, and when I say we mess with it, we do one of these three things, okay? Now Q is not K, because we messed with it. I went in there and I did something to make Q equal not K. The system doesn't like that, right? The system wants to be at K. So the system responds by counteracting this change, and we spontaneously return to Q equals K. All right? So we're going to go through these three different types of disturbance and look at how they impact equilibrium. All right? The K is the same, okay, for these first two, but we will make a shift. All right? So let's look at a problem here. The reactant product concentration. All right? We're looking at our Haber-Bosch. Okay, N2 plus 3H2 makes 2 ammonia molecules. All right, what we have here, this is time on our x-axis and our partial pressures on the y-axis. Okay, so notice that we don't have any change in concentrations here, so I can make the assumption that Q equals K. We are at equilibrium. Okay? While we're at it, let's write out what K equals. Since it says pressures on the y-axis there, let's write it in partial pressures. We've allowed this to come to equilibrium, right? And now we do something. We're going to add some H2. All right? Now all of a sudden, Q is not equal to K. Because I just spiked this number, right? I went in there and I had a port and I was increased the pressure of H2. I did something to the system. I added H2. Now Q is not K because this number is too big, right? So Q is now going to be less than K. Because I added H2. This is specifically for adding a reactant, okay? So how does the system respond? It wants to get back to equilibrium. It wants Q to equal K again. So what does the system do to reach equilibrium when Q is less than K? We consume some of our reactants. So this pressure's going down. So is N2. And we make some product. So overall, we added reactant, and the system responded by making product. Or I could say by consuming reactants. Yeah. Yes. If I add reactant, I am always going to be making that denominator bigger. And so my Q will always be smaller as a result of adding that. Specific to reactants. Okay. All right. So again, I like to view this as a seesaw here. So what do? We're at K equals Q here, right? It's balanced. If I put in reactant, that throws the balance off, right? Now all of a sudden it's not at equilibrium. Now the system is locked, right? I don't have the system, I'm not disturbing it anymore. I can't go in and pull things out, okay? The reactant, the only way we get back to a balanced situation is if the reactant converts to products, okay? That's the only way this happens, all right? That is not very useful to us, I will say. Like the concept of being like, hey, if you put in more reactants, we can make more products. We're like, great, but like, I'd really just like to make this a more efficient reaction without having to keep adding in reactants. So the very elegant way of doing this, if you want to make your reaction more efficient and make more products, okay, is to take out product, okay? So here I have K greater than 1, which just means that we favor products at equilibrium. If I can figure out a way to isolate the products and pull it out, right? If I take that, then I'm now out of balance. I have too many reactants because I pulled products out. This is a lovely, easy way to make your reaction move forward. If I can pull products out, that means I'm going to have to take some of my reactants and make more products, okay, without putting in any additional inputs, okay? So this is like, if you're doing good chemistry, this is the way to go. Because if I'm going to pull those products out and I'm going to store them and keep them nice and safe. And then that forces the reaction to keep going forward. All right. So here are the rules for adding or removing reactants or products, okay? So if we add a substance, okay, this is specifically for adding, okay, and we're adding it to a system that's already at equilibrium. The system responds by consuming whatever we added. So if we add reactants, we're going to consume those reactants, which by nature means we are making products, okay? If we add products, let's say for whatever reason we want more reactants, okay, if I add products, we'll make more reactants, okay? So let's add reactants, make products. I want to remind you of the language around this. So if I add reactants, make products, you might see this written as a shift right, okay? Add products, make reactants, shift left. Okay. Then, of course, we don't have to just add a substance. We could try and remove substances from our reaction vessel. And again, the system responds to counteract that change. So if we remove reactants, we'll make more reactants. Okay? If we remove products, we're going to make more products. This is the one that makes the most sense. How do we employ Le Chatelier's principle to our advantage? That's really useful. If we can pull those products out, we force the reaction to keep going. Okay? So that's our one set of disturbances. We can mess with the amount of reactants and products. Okay? Now, we have another option. We can change the volume and thus the pressure. This is only going to work for gas phase reactions where we have a non-zero delta N. Okay, so we have to have a change in the number of gas phase particles. for this to work. All right, so we're looking at 2A converts to B. All right, here's our initial volume. We are at equilibrium here. There is some pressure associated with that. So I'm going to call that this total pressure PEQ for just that we're at an equilibrium pressure, okay? Now, what happens if we condense the system? Maybe this isn't a piston, and I push down on the piston, right? I collapse the volume. I'm going to raise the pressure of the system. Well, our equilibrium, our reaction doesn't like that. It wants to be back at that original equilibrium pressure. So when I decrease the volume and increase the pressure, our system looks for a way to bring the pressure back down. And the thing that it can do is convert 2A to B, so it can drop the number of moles. That will lower the pressure, okay? So this favors the side with fewer gas phase molecules or particles. Okay? So like I condense it, I really increase the pressure. The system doesn't like that increase in pressure, and so it reduces the number of moles. Okay? That's why this only works if there's a delta N. Because if there's no change in moles, then it doesn't matter if you go to the reactants or products. The pressure is still the same. So we're going to reduce, this is reducing number of moles. The same is true, but going the opposite direction, where let's say I have that piston and I pull on it and I expand that volume. Now our pressure decreases, okay, our pressure is low, and our system actually would like to raise the pressure, and so it's going to favor the side with more moles. In this case, it's going to favor A. So we're going to take some of those B's, they'll split up, and we'll make more A's, okay? So this increases the number of moles. Okay, I want to prove to us, I want you to prove to yourselves that this is true. Okay, so once you get these notes down, I'm going to have you do a practice problem. All right, so let's check the math. We have initial conditions, so at 472 degrees Celsius, Kp for the hot gavage is 2.79 times 10 to the negative fifth. These are equilibrium pressures that I've listed here, okay? In other words, for yourselves, you can go and calculate out that when you have 0.166 squared divided by 7.38 cubed and 2.46, this should equal the 2.79 times 10 to the negative fifth, okay? Now, the part I want you to show me is that when you decrease the volume by 1/2, the pressure for each component doubles, right? There's that PV equals nRT, so if I'm going to have the volume, the pressure is going to double. And now I have these new pressures. So I want you to calculate what Q is now at these pressures, and then tell me how the system responds to this change in volume/pressure. So no time like the present, pull out your calculator. This could be a question on the exam. What is Q for these new conditions? Plug the numbers in. Make sure you aren't making a silly calculator punch error. my new Q. All right, before Q equaled K. Now, hopefully, you calculate something other than 2.8 times 10 to the negative fifth. I'm going to have 0.322 squared divided by 14.76 squared times 4.92. I got 6.6 times 10 to the negative 6. Yes? Yeah. Say it louder.
Will the 14.76 be cubed instead of squared?
Yes, it will be. I just wrote squared instead of cubed. And I did it right, and hopefully we got the same answer. Yes? Okay. So now you say Q, that is a smaller number, so Q is less than K at these new conditions. The system doesn't like that. The system wants Q to be K. It'll spontaneously do that on its own. So at this new pressure, at this new volume, I don't have enough NH3. So by doing this, I am going to make more products. Okay, when I make this adjustment, I will have more NH3. All right, so this produces a shift right. That tracks with what we said earlier because this side has fewer molecules than the left side, right? So decrease the volume, increase the pressure, the system is going to go to the side that has fewer particles. And we had a delta N here, right? We had 3 plus 1, so 4 gas molecules to begin with, and at the end we only had 2. Okay? So that is a quantitative question. This is maybe the more conceptual piece of it, of saying like, hey, by decreasing this volume, will that shift the equilibrium right or left? And this is to the right. All right? So just make sure you feel comfy with increasing the volume favor the reactants or products in this reaction. N2O4 degrades to 2NO2. Okay, which side are we going to favor when we increase the volume? So circle that for yourself. Hold it in your mind. Increasing the volume would mean a decrease in pressure. The system wants to counteract that decrease in pressure, so what can it do? It can raise the number of moles, which would be the product side, right? More moles. Would decreasing the volume favor the reactants or products? For H2 plus I2 goes to 2HI. This, I cannot control this reaction or like tip the scales in my favor if I want to make HI using volume or pressure because there's no delta N. Delta N is 0, so I can't do this. It doesn't do either. Okay, pressure is not a variable I can use here. Then lastly, if I increase the pressure of a reaction vessel by adding argon, okay, but the volume remains the same. I'm just pumping in argon and raising the pressure. Would I change the equilibrium concentration of N2O4 or NO2? Okay, so like hold an answer in your head, say yes or no, maybe come up with a reason. Okay. Okay, we're looking back at this reaction up here. And I notice that when I write out Kp, there is no spot, there's no seat in this equation for the pressure of argon. So if I'm not changing the pressure of one of my components, then I'm not disturbing my equilibrium. So I can add in argon all I want, and that's not going to have an impact here, as long as those pressures or those concentrations are not changing. Okay? So no change. All right, so that's pressure and volume. Now we're on to our last disturbance, okay? changes in temperature. These are different, okay? The last two, we didn't change the value. The equilibrium constant was constant. Constant divided by the reverse rate. I often ignore, but I'm leaving here today. E times negative delta E divided by RT, okay? Remember we said that whether or not this reaction was exo or exothermic had a really big bearing on the value of K. Importantly, notice that T is not dropped out of the equation. So temperature is the variable right the value of K. So changing temperature right? How it changes it will depend on if the reaction is exothermic or endothermic. Okay, so let's consider then delta E itself is negative, right? We have a drop in energy, that energy is released, we think about that as being negative. So we have a negative of a negative up here, okay? So equation K will be so I'm just saying like that's a negative of a negative, where I'm going to have a positive value up there. And that's only true if it's exothermic. Okay, so when I increase T, okay, if I were to turn up the temperature on an exothermic reaction, then I am making the exponent a smaller positive number. Okay, therefore K will go down, and it'll be a shift towards the reactants. That is only true if it's exothermic. The reverse logic holds that if I lower the temperature, okay, if I make that denominator smaller, then I have a bigger positive number and K is getting bigger. Okay, so when I lower the temperature on an exothermic reaction, that should, no. Failing. Now we're back. Okay, then that would lead to an increase in K. Okay, a shift towards our products. So for an exothermic reaction, if I want to favor products, I should lower the temperature. Okay? Let's run this back, but we're going to do it on the endothermic side now. Okay, the key endothermic reaction, our delta E was positive. Right? And so now in our exponent, we have a negative number. Okay? So when I go to raise T, all right, when I raise T, I'm going to have a smaller negative number, which means that I'm going to have a larger K. Okay? And then the opposite is true. If I lower the temperature, I'm I'm going to lower K. All right. I don't think this is going to be you don't need to think on these quantitative lines. This is just like if you want to see how this relationship plays out, this is the math, okay? How these variables relate to each other. We have an easier way of dealing with temperature, all right? Thankfully. So let's look at this reaction here. All right, we have an endothermic, wait, do people need that last slide back up? Are we good? Good? Okay. Here I have an endothermic reaction. How do I know that? Heat is on the left side. It is a reactant, all right? So that is how I'm going to recommend you think about this in future problems. If it is endothermic, heat is a reactant. And so we can think about changing the temperature as adding or taking away a reactant. So now we can use the same framework that we use for adding, like increasing the concentration or removing the concentration of a reactant. We can now do that for heat. So in this case, when it's endothermic, if I increase the temperature, this is basically adding, actually let's do it in red just because I feel like that makes more sense to me. Increase temp, right? That's adding a reactant, right? Because we said this is endothermic, so I need heat to make this happen, so I can think of heat as a reactant. When I add reactant, the system changes. It counteracts it by consuming that added reactant, so it makes more product. Right? In the same way that if I added more of my chemical reactants, I'd say, oh, we need to make more products. Right? Now I'm just going to think about heat that way. Okay? If I decrease the temperature for an endothermic reaction, that's like removing a reactant. So we'll make more reactants. Okay, this is a nice colorful reaction here where we see it's purple. We have both blue and even equal balance of our blue. Pink. When it's cold, we have more of the reactant, which is pink, right? Taken out of the reactant, which is heat, okay, and we force more reactant to form, okay? Same opposite going the other direction. Add in the reactant, which is heat, we make more of our product. Here are your rules for how temperature changes these things. So if the reaction is exothermic, you're going to think about it as a product, okay? So if you increase the temperature, that's like adding a product. And so we're going to consume product if we add product, okay? Decreasing temperature is like removing a product. Okay, so the system responds by making it. And then the opposite is true for endothermic because heat is a reactant. So that's the example we just walked through. So increasing temperature would be like adding a reactant, okay, which means we're going to make more product. Okay? Decreasing the temperature would be like removing the reactant, and so we have to respond by making more reactant. All right? Try and get comfy with those. Know that you cannot assess how temperature impacts a reaction unless you know whether it's endo or exothermic. You cannot answer that question without knowing that piece of information because it does different things. All right? So here again, this is like shifting. We are actually changing K. Okay? So originally it was here, it was exothermic. If I increase the temperature, it is moving the pivot point. So at this higher temperature, I'm going to need less product to balance myself out. Okay. The reason we often, in this chapter, we talk so much about the Haber-Bosch process is because this was optimized using these principles of equilibrium. All right, it was really important that we take N2, which is all around us, but we don't process, right? I don't N2, I just breathe in and then breathe out. Whereas NH3 is used as a fertilizer, and I did double check this, that about 50% of the nitrogen atoms in all of our bodies have been through this industrial process. Okay, so like it is responsible for the growth of the human population. If we didn't have all of this NH3 that we made, we would never be able to grow crops necessary to support our population. All right, so how did Haber and Bosch, they received a Nobel Prize for this. How did they figure this out? Okay, so they wanted to favor NH3. Okay, if you've been paying attention to the numbers, you might have noticed that our K is actually quite small for this reaction. So we needed to really tip the scales in our favor to make more NH3. So what did they do? All right, as temperature increased, okay, so they were noticing on this axis here, as they increased temperature, the percent of NH3 decreased. Okay, so that told them they should keep it at lower temperatures to favor NH3. That means it was exothermic. It's an exothermic reaction. I can draw that conclusion from how the equilibrium constant responded to the change in temperature. Okay, so the ideal would be to keep it at lower temperatures. Okay, low temp is preferable. Still hot because it's 400 degrees Celsius, but not 550. And then the other thing they did was they decreased the volume so that they could increase the pressure. Okay? And they had optimal production at lower temperatures and higher pressures, and the higher pressure is because we have fewer molecules on our product side. Okay? So combining those two, they optimized this reaction and also put in a catalyst to make it go quickly. And they like revolutionized humanity because now we can support some, 8 billion people in theory. All right? So this is like why this equilibrium stuff matters. All right? So take a beat. I want you to look at this reaction. I've given you the delta H that tells you if it's endo or exothermic. Assess which direction the reaction goes based on these 4 disturbances. Okay. Imagine the system, we've put some PCl5, we have PCl3 and Cl2, it's in there, it has reached equilibrium. All right, Q equals K. And then I go in and I do I mess with the system, all right? I can somehow preferentially only pull out Cl2, all right? If I take Cl2 out and I drop the concentration of Cl2, this number is smaller, right? I have just gone in and I've like yanked out Cl2s. So now in this scenario, my Q is too small. My Q would be less than K. So to get back to equilibrium, I should make more products, which we usually talk about as a shift right. If I decrease the temperature, the thought process here is, hey, this was endothermic because delta H was positive. So I should think about this as heat as a reactant. So when I lower the temperature, I am essentially pulling out reactant. When I take out reactant, I have to make more reactant. So this would be a shift left. Okay. Again, I cannot make that judgment without knowing the sign of delta H. All right? If I change the volume of the reaction, if I increase it, okay, I've increased the volume of the reaction, that decreases the pressure, and the system responds by making more moles. So then you look at your reaction and you say, which side has more moles? My products have more moles. I have 2 instead of 1. So this would also be a shift right. I would make more product. Okay? If I added PCl3, right, this number here gets bigger. So I would have a Q is greater than K situation. Too much product. I would need to make more reactants. Okay, so that'll be a shift left. Yeah. Uh-huh. Yep. Okay. One of your post-lecture questions is Le Chatelier principle. This is very likely how you'll get this question on the exam. We'll give you a reaction with this information, and then we say, hey, we make all these disturbances. How is that going to impact the amount or the balance? Am I going to need to make more reactant or more product? Or does it not change anything at all? Okay? Last little tiny bit from chapter 15. What does a catalyst do to equilibrium? All right, we talked about catalysts a lot in chapter 14 because they speed things up. We know they speed things up because they lower the activation energy, right? This changes. But importantly, our delta E or delta H does not change. Okay? Catalysts don't change my beginning and end products. And remember, we have written that K, big K, equals our frequency factors times e to the negative delta E RT. A catalyst doesn't change that number. And so while a catalyst speeds up the reaction, if we put a catalyst in, we will get to equilibrium faster, but the equilibrium will be the same. Okay? So we get to the same place. We're going to the same destination, driving faster. Okay? That's what's represented here. All right, we're always getting to the same place. All right, that's all I have for you about chapter 15. With our last 10 minutes, we are going to start chapter 16. Fun fact, though. Who remembers acids and bases from 1210? Oh, that's joyous. I feel the joy emanating from you. All right, so bear with me. We're going to get into our definitions, all right? We're going to do the definitions now so that on Thursday we can start the fun stuff about acids and bases, all right? All right, complain for 10 more seconds about acids and bases, and then let's bring the side convos down. All right. Our first definition for acids and bases comes from Arrhenius. He just really did a lot of stuff. And then he was like, I'm going to name it after myself. All right. So he said that acids increase or produce H plus in aqueous solution. So it was tied to it being in a water solution. All right. And he said that bases produce OH minus in, again, aqueous solution. So these original definitions were tied to this happening in water. All right? We want to expand that. Okay, we will not be living here. So side confos down, please. Thank you. All right, so we will really be spending most of our next 2 chapters thinking about Bronsted-Lowry definitions, all right? Again, we didn't like this original definition because we had to be an aqueous solution, so we're going to expand this, all right? Say a Bronsted-Lowry acid is anything that donates an H+, all right? I have a lot of different ways of saying this, that thing. I might say H+. I might call it a hydrogen ion. It is actually just a proton, right? Because if I have a standard, like the most common hydrogen atom, it's just 1 proton and 1 electron. So if I take the electron off, it is literally just a proton. All right, so you might hear me call it a proton. And an acid is anything that accepts H+, okay? So this now doesn't depend on being in water, although for most of the next 2 chapters, we will be in water. All right, so let's see these in action when you put a Bronsted-Lowry in water. We'll start with the acid. All right, so HA donates a proton. So let's look at this. There's HA, that's our acid. Okay, it is interacting with water. And water, let's actually draw this out. So HA, we've got our water. The oxygen there has 2 lone pairs, or 2 non-bonding pairs of electrons. Those electrons come over, take the proton. The shared electrons in this bond are given to whatever A is, whatever the rest of that acid molecule is, okay? So A, so that's the donating or giving of the proton, all right? And then we wind up with our H3O+. This is called the hydronium ion, and it is the hydronium ion, and it's really what the system looks like in water, okay? So there's our HA. It has that extra proton to give. It gives it away to H2O, and we make H, quote-unquote, right way to draw this or to write it out. It's the most accurate. You will often see us be very lazy and write this, where I drop water out of it, so I don't write water explicitly. I just say, it's aqueous, but H+ doesn't exist in water. It's always going to be attached to a water molecule as H3O+. And in fact, it will be an even larger network where that positive charge, that extra proton, gets shared across a bunch of different water molecules. Okay, and so this is why water is really good at taking those protons, because it shares the charge, okay? It can spread out over these large networks. All right, so that is a Bronsted-Lowry acid. A Bronsted-Lowry base is the thing that takes the proton. It accepts it, all right? So this B here has a lone pair that I didn't write, but it has to have a lone pair because it will use that extra set of electrons, well, unbonded, non-bonded electrons, to make a bond with one of these hydrogens. All right? So it's using its extra pair of electrons, or non-bonded pair, to take this hydrogen. These electrons are then given to OH, and that's how we wind up with BH plus and OH minus. So this is consistent with what Arrhenius said. Hey, a base in water should make OH minus. And this is how it does it. And we think about it as a proton transfer. Okay, that the base is going to take that proton from water. It's really good at doing it, and we generate that hydroxide ion. All right, that's the hydroxide. All right, so take a look at this reaction here. So now notice that I'm in the gas phase. I don't actually need to do a Bronsted-Lowry acid-base reaction in water. I could just transfer a proton between two species. Identify which is acting as the acid and which is acting as the base. When you get these questions, the acid and base should be reactants, right? So you're not going to pick one of your two products here. Okay? So you're going to remember, you're going to say an acid donates a proton. So who gave up a proton? Okay? So I compare across the reaction arrow. Say HCl became Cl minus. It lost its electron. It must have given, its proton. It must have given it away. So HCl was my acid. NH3, I look at it across the arrow. It became NH4 plus. Therefore, NH3 was my base. It accepted that proton. It took it. Okay? These two things have to happen together. Okay? This is my last slide. I promise. I'll end here today, okay? We cannot have an acid act as an acid without having somebody else act as a base. If you give away a proton, somebody must have taken it. Therefore, someone acts as an acid and someone acts as a base. All right? We will talk more about amphiprotic substances, but these are things that can do both. And